Today, we're totally bridging the gap between everyday classical physics and cutting-edge tech. We are heading straight down into the bizarre, incredibly tiny, microscopic quantum realm. So grab your focus because we're jumping right into it.
Right off the bat, I want to ask you, what if I told you sound waves could actually fix quantum computing? I know, it sounds a bit like science fiction, right? We normally just think of sound as the music in our headphones, the traffic out on the street, or a conversation with a friend. But manipulating the fundamental properties of sound, something that is just so familiar to all of us, could genuinely solve one of the most highly complex bottlenecks in modern science. Keep that in the back of your mind as we go through this today.
Okay, let's dive into this. You know how gravity and basic physical laws just make sense in our natural, everyday world? Well, the second we shrink down into the internal components of today's microprocessors, that predictability completely falls apart. Inside those chips, everything operates according to the unique and, frankly, incredibly complicated rules of quantum physics. It's an entirely different rulebook.
So here is our roadmap for the explainer today. We'll start with 1. The quantum computing problem. Then 2. Enter the acoustic atom. 3. Mimicking real atoms. And finally 4. Building future technologies. Don't worry, we're going to break this down step by step.
Let's kick things off with Section 1, the quantum computing problem.
To truly get why this new solution is so brilliant, we first need to look at the massive scaling crisis engineers are facing right now. As the chips powering our computers, our sensors, our medical equipment continue to shrink down to unimaginably small sizes, we're hitting a severe wall. Controlling quantum-scale systems is just getting exponentially harder. At this microscopic level, quantum information is incredibly fragile, and its lifespan is super short. Because of that fragility and just how densely packed these shrinking chips are getting, signals end up unintentionally interacting with each other. Honestly, it's a scalability nightmare. And this brilliantly illustrates the real issue. When you shrink technology down this small, the environment becomes completely chaotic. The enemies of the quantum scale are just constant. You've got vibration, heat, material defects, and ambient electromagnetic noise everywhere. All of these factors have a massive detrimental impact. They are constantly threatening to destroy those super fragile quantum states that we actually need to process information. The quantum realm is basically a really tough neighborhood for data.
Which brings us to our solution in Section 2. Enter the acoustic atom.
So, a team of researchers at Virginia Tech working with the Oak Ridge National Laboratory recently published a totally groundbreaking study in Physical Review Letters. They've offered this incredibly elegant fix to the exact problem we were just talking about. They've developed the acoustic atom. This is a microscopic, chip-scale device that traps and controls sound waves in ways that mimic the behavior of real atoms. Seriously, think about that. It mimics real atoms, but it does it using sound. Instead of trying to fight that chaotic quantum noise with traditional electronics, they're just fundamentally changing the vehicle they use to process the signals.
Linbo Shou, the assistant professor at Virginia Tech, who actually led this research, explains it beautifully. He says, in nature, an atom has distinct energy levels that electrons can jump between. It's a fantastic analogy. It anchors this crazy new invention to something we already understand from basic chemistry. Just like an electron naturally jumps between specific energy levels, this new device forces sound to recreate that exact same structured environment.
Now, what's really interesting about this slide is the emphasis on sustainability and the physical footprint. Acoustic waves offer a remarkably compact way to process and route signals. And when you are dealing with quantum and microwave tech, space is literally everything. But even more crucially, acoustic waves can actually hold on to information, or energy, for far longer than traditional electromagnetic waves can in these tiny environments.
Moving right along to Section 3, Mimicking Real Atoms.
So we know what it is, but how exactly does this device trick the universe by acting like nature? Well, the mechanics are fascinating. Step 1. The researchers apply electrical fields directly to the device. Step 2. Those electrical fields are used to drive transitions between distinct acoustic energy levels inside it. And finally, Step 3. Through those forced transitions, the acoustic waves successfully start imitating the controllable behaviors we see in real atomic systems. They are effectively forcing sound to act like distinct atomic energy levels, creating a perfectly controlled environment right there on the chip.
So the crucial point is why this is such a game changer. Look, standard electromagnetic waves are notoriously hard to confine at these tiny scales. They leak, they interact, they degrade, it's a mess. Acoustic waves, on the other hand, can be tightly confined to a microscopic footprint, and they hold on to their information much longer. This simply makes acoustic waves a vastly superior vehicle for exploring entirely new pathways in future signal processing and quantum systems. Now, actually, I should clarify, we aren't totally at the finish line just yet. Right now, researchers are using classical, coherent microwave sources to drive these acoustic waves. The ultimate long-term dream is to get this technology all the way down to the single phonon level, which is the absolute smallest quantum unit of sound. But the fact that they are proving this concept works right now using current microwave sources, that is a massive leap forward. The foundation is officially laid.
Let's wrap things up with Section 4, Building Future Technologies.
We've been zooming way in on the microscopic quantum realm, but let's zoom out for a second and look at the macro-level ripple effect this acoustic atom is going to have on everyday life. Because these waves are so incredibly compact and stable, this breakthrough is going to feed directly into some super vital tech. We are talking about way smaller microwave communication components for your devices, radically improved signal routing. It opens the door to powerful analog computing systems, totally new interfaces for quantum hardware, and it will even revolutionize highly sensitive sensing tech. Controlling these sound waves is basically going to impact everything from the GPS in your car to global telecommunications to medical imaging and even quantum AI.
Professor Xiao perfectly encapsulates the vision for the future here. He states, ultimately, we hope this platform provides a new, highly compact way to process signals and perform analog acoustic computing directly on a chip. And, with upcoming collaborations already planned across multiple Virginia Tech research centers, the push to make this sci-fi concept a reality is happening incredibly fast.
I want to leave you with this final, provocative thought today. If manipulating the basic, fundamental properties of sound can literally rewrite the rules of computing and solve our massive quantum scaling crisis, what other everyday natural forces might be out there just waiting to unlock our quantum future? It's an absolutely incredible time to be watching the intersection of classical physics and the quantum realm.